Hello and welcome to this video. In this video we're going to be looking at magnetic flux and magnetic flux linkage. So in all of the other fields we have defined things like their potentials and their field strengths, and that's what's given us all the information we need to know about the gravitational and the electric fields. However, for magnetic fields we have new things that we want to introduce, and now we introduce these purely because of the uses of magnetic fields. The use of electric fields and gravitational fields don't really require us to introduce the ideas of gravitational flux or electric flux. But magnetic fields, because of our whole use of magnetic fields is electromagnetic induction, we'll find that introducing this idea of flux and flux linkage will actually help us to understand what's happening when we get onto that side of the topic. So this video is just going to introduce us to the idea of what flux is, or what magnetic flux is, and also what magnetic flux linkage is. Now to start with, I'm first going to set up this idea of just a single coil. So we take a single coil of wire, okay, and I'm going to make it a circular coil, and I'm going to have a current that's going to flow this way, and it's inside a magnetic field. So I'm going to draw the magnetic field like this, as we've done in the previous videos, remembering that these crosses mean that the magnetic field is uniform and going into the screen. And the whole point of this is this B, what we've defined this as, is the magnetic flux density, right? So B, or what we've said is the magnetic flux density, we said we could refer to it as the magnetic field strength. This is the magnetic flux density. Now, we know this word density from materials is per unit volume, right? The density of a regular thing is mass over volume. So the magnetic flux density, we would assume, is going to be over some sort of volume. But what we actually find is that it's more useful to have a linear density in this case. So what we mean by a linear density is this is the amount of flux per unit area. So this is flux per area. Now what does flux actually mean? Well, the flux is just a magnitude of the amount of the magnetic field that is traveling through it. You could think of this, if you were to go back to the idea of an electromagnetic wave, that would be some sort of radiation. So you can also think of flux as an amount of radiation incident on the surface. And what we're saying here is we're taking just the magnetic part of the electromagnetic wave. We're saying how much of that magnetic field is actually incident on this surface. And that means that using this idea of what the magnetic flux density is, we can already define what an equation for flux would be. So if flux is just almost a measure of the total amount of the magnetic field, through a surface, and we already have this idea of a flux density, which is per area. We want to get that flux density and multiply it by the area that it's going through, and that's the total amount of the magnetic field, or that's the flux that's traveling through this. Now flux we're usually going to note with this symbol phi, and what we're going to say is we can make this equation, therefore, that the flux is equal to the magnetic flux density multiplied by the area. And this is the equation that is written on your equation sheet for the magnetic flux. Now, this doesn't seem like it's very useful at this point because we haven't really gone into the uses of magnetic flux yet, but what you'll find when we get to the electromagnetic induction, that this is a very, very important thing, because any change in this flux is what actually causes an EMF to be induced, and we'll talk about that in a later video. So this gives us an idea of flux. So now we know what flux is, but what exactly is flux linkage? And what we can say then is, well, we said this density could be per unit volume, right? Because that's generally what a density would be. We're assuming this is a linear density in this case because we have a single coil of wire. We're assuming that the thickness of the coil or the thickness of the wire is negligible in comparison to the actual area, the cross-sectional area. We're saying the cross-sectional area is probably going to be a few centimeters squared. You've got a thickness of about 1 millimeter. It's not really going to make a difference if we do it by volume or by area. But then we have to take the idea that obviously not always are we going to have a single coil of wire. Sometimes we have solenoids. So now we need to introduce this idea of what a solenoid is. And a solenoid is if I take this single coil of wire and I wrap it round so I get multiple turns in this coil. So it looks something like this. Now obviously this isn't a great drawing of a solenoid, but you get the idea. This is a current carrying wire, and where I'm looking head on here, I'm looking at the side here. So I have multiple circles. I'm going to say I have n amount of turns. So this is just some number of turns that I have. And I've drawn this purposely spaced apart. Obviously, if we wanted to actually make a solenoid, we wouldn't have bits in between it. It would all be very connected. It would look more like this. But then that's not very visual, so we'll keep it like this for now. And we assume that the distance between them is negligible. Now what this means is that if I look at the flux in just a single one of these coils, I can say that that's just the magnetic flux density multiplied by the cross-sectional area of that coil. And that would make sense. The idea then is that actually, if I were to turn this on its side, I have n amount of circles that it's actually passing through. So I have n amount of surfaces. Now if I'm looking for the total amount of magnetic field that passes through a surface, and I have n surfaces, so I need the magnetic flux passing through each of those surfaces. And this is what flux linkage is. So flux linkage is just taking flux and saying I'm actually going to have multiple surfaces for it to travel through, and you guys will only ever actually have to look at this in terms of solenoids usually. And so what I can say is flux linkage we don't have a special symbol for because it's just going to be the flux. So flux linkage is the flux, which is phi, just multiplied by the number of turns on the coil. And this is going to be the first half of the expression that you get in your formula sheet. But this isn't the full expression. Now, to complete this full expression, we have to go back to this idea of Fleming's left-hand rule that we originally looked at. And we said that we had this FBI rule, where F is, let's, for example, say that it's vertical in this direction, and then we have the B field that's going to go in this direction. And let me label these. This is F and this is B. And if you were to line up your left hand along with this, you would have the current coming towards you. Okay, now what we're saying here is that everything is perpendicular to each other. That's the whole idea of a left-handed system. But in reality, this isn't always the case. I could rotate any of these coils so that it's actually at some sort of angle to the system. So then what happens to the flux linkage if I then just rotate this a little bit? How does the flux change? How does the flux linkage change? And actually what's going to happen is the area that we have is going to change. So let me set up another example. I am going to simplify this down to just a single coil of wire because obviously the flux linkage is just multiple coils, so all we'll do is just multiply the flux that we get from the first one by n, and that will give us our flux linkage as well. But now let's set up this kind of idea that I'm going to have the same uniform coil or uniform B field. So I have this magnetic field, and initially I'm going to have a let's go with a square, right? Let's have a square coil in this case, just to make the maths a little bit easier with the areas. And at this point I have, if I want to look at the cross-sectional area, let me say that this is A, and this is also A because it's a square. That means that my cross-sectional area that the flux is passing through is just A squared. which is a maximum in this case. Right, now I'm going to say, let me choose this axis, okay, and I'm going to rotate it around this axis. So it's going to start spinning on its own axis. After some time, if I turn it by 90 degrees, so if it changes by 90 degrees, I then, from the same perspective, I'm no longer going to see a full area. It's not going to pass through the full area of this. I'm just going to see the side of this, which means actually my current area that it's passing through is 0. Okay, and then I'm going to rotate it again, and I'm going to get back to this, and then I'm going to rotate it even further, I'm going to get back to this, and then I'll finally get back to having a full area, and I'll leave you to prove that to yourself. But then we have to think, how is the area actually changing as we rotate it around its system, as we alter its alignment with this magnetic field, which is what we're doing. How does the angle affect the flux that's passing through it? And so what we're going to say is, let's actually just plot a graph here of the area and the angle. Okay, so the area and angle and how that's changing. So let's call this 0 degrees. We haven't rotated this by any amount yet. So if we rotate it through 0 degrees, we start with a maximum. So we're going to start up here with a squared. If I rotate it through 90 degrees, okay, and I am keeping these in degrees, not radians for now, I get to 0. So I need to get to 0 at this point. If I rotate it through 180 degrees, now the key with this is that when you do the complex maths on this, we're not too worried about the complexities of the vectors and maths on this, but this area is actually a vector, so it does point in a specific direction. So when you rotate it 108 degrees, it's now pointing in the opposite direction. You don't have to worry too much about vector areas for now. For those of you who want to do it at university, it will get explained to you when you're in university. But this means that I'm going to get a maxima again, because if I rotate it through 108 degrees, my maximum flux is still maximum, right? My area is still maximum, so I have a negative maximum because it's in the opposite direction, where this is going to be minus a squared. If I rotate it 270 degrees, I'm then going to end up with 0 again, because it's going to get back to this situation, and 360 degrees, I get back to the starting position, which means I'm back here. Now, for those of you who are pretty hot on the maths, you will have already noticed this is just a cosine graph, right? So I can change to 0 down here. It's obviously not going to go linearly, because if I make a small change at the beginning, it's not going to result in a massive change in area, but at the end, a tiny change in the angle takes it from being some value to being exactly 0, so the gradient of the change actually does change. I'm then going to go down to 180, I go back up to 270, and I go back up to this. So actually, what I find is that my area over time, as I change it, is actually the area of the cross-section multiplied by cos of theta, okay? Because that is the function that this area is taking, okay? So this then gives us an idea of, if I change the orientation of this coil with respect to the field lines, I'm then going to change the area, which means I'm therefore changing the flux, okay? And this means that I can go back and say that if actually the flux linkage, or let's just say the flux itself was just BA, then that means that if I have the flux linkage, or actually I could substitute in A for this A already, let me call this A naught for the maximum, so A naught is equal to A squared. Okay, so if this is A, I could substitute this in already for A naught cos theta, or I could say that the flux linkage, which is the flux times N, is actually BA times N times the cos theta from the A. So I've just multiplied the flux by N, and I've substituted A for A cos theta. And this is your expression for the flux linkage that you get in your formula sheet. Now, what I've done here is a very specific example, rotating around a very specific axis. I've done this because it will then be clearer in future videos what happens with the electromagnetic induction. However, I could have chosen any axis to rotate this around. I could have rotated it around this axis. I would have ended up with the exact same result. I could have rotated it, well actually I couldn't have rotated it around this axis going through the center, coming out or into the plane, because if I rotated it around that axis I'd end up with the same area all times. But now you have a good idea of what the flux is in a magnetic field. It's just the total amount of magnetic field that's passing through a single surface. You know the flux linkage is now extending that through some sort of solenoid, which means that it's going to get its own amount of flux linkage, which is just the flux multiplied by the number of coils. And we know that if we can change the alignment with the magnetic flux lines or the magnetic field lines, you will then end up with a different value for the magnetic flux, because I've changed the area that the field is actually passing through. Thank you for watching.